Hello everyone, we are Abhinav Anand and Pramansu Pradhan from VNIT Nagpur. This project presents a model-based approach to static and dynamic obstacle avoidance for UAVs, developed entirely using Simulink for the Mathworks Simulink Student Challenge 2025. Our goal is to demonstrate how physics-based modeling, perception, and planning can be integrated into a single closed-loop autonomous system. UAVs today operate in highly cluttered and unpredictable environments, such as urban areas, forests, and constrained airspaces. The challenge is that most existing algorithms handle either static obstacles or dynamic intruders, but struggle when both appear simultaneously. Our objective is to develop a holistic algorithm within Simulink that prioritizes low latency and safety, while addressing both global and local navigation complexities. To solve this, we adopted a digital twin-based architecture in Simulink. The system is divided into 4 layers: plant, perception, logic, and control. These layers interact in a closed-loop simulation, allowing physics, sensor feedback, and planning decisions to evolve together in real time. This modular structure also makes the system scalable and hardware-ready. We began by modeling the physical quadrotor dynamics. A lift allocator converts collective thrust and attitude moments into individual motor forces, which are fed into a 6DOF quaternion-based rigid body model. This block outputs realistic position, velocity, orientation, and body rates, ensuring that all higher-level logic operates on physically valid data. This slide shows the actual Simulink implementation of the plant model, including thrust inputs, wind disturbance injection, and actuator saturation. By keeping the dynamics model realistic, we ensure that any avoidance or planning behavior we observe is feasible on a real UAV. For perception, we modeled GPS, IMU, and barometric sensors. These measurements are fused using an extended Kalman filter, which filters sensor noise and outputs a clean 10-state estimate vector, including position, velocity, and orientation. This estimated state becomes the foundation for obstacle detection and planning. Here, you can see the full EKF implementation in Simulink. This block continuously updates the UAV state using multi-sensor inputs, ensuring robustness even under noisy or partially unreliable measurements. To handle dynamic obstacles, we introduced vision and radar detection generators. These detections are processed by a global nearest neighbor multi-object tracker, which associates new measurements with existing obstacle tracks. Each tracked obstacle is inflated into a safety bubble, accounting for uncertainty and latency, enabling safe interaction with moving objects. The core decision-making happens in the local planner. Based on the goal position, static map gradients, and dynamic safety bubbles, it computes a desired velocity command. A safety gate layer continuously checks proximity and triggers deceleration or hover modes when required. Finally, PID controllers convert these commands into roll, pitch, and thrust actuation. We validated system robustness through multiple tests. In the first test, a sudden wind gust is applied. The controller quickly damps the disturbance and stabilizes the UAV. In the second test, the UAV mass is increased without changing thrust, causing failure to lift. This negative test confirms correct physics modeling and actuator saturation behavior. In this test, we intentionally misalign the static map from real sensor data. The system correctly prioritizes real-time sensor feedback over the preloaded map, adjusting its position to maintain true safety distance. This demonstrates resilience against mapping errors. We then tested dynamic avoidance scenarios. In a head-on intruder case, the UAV performs an early lateral maneuver while maintaining a positive safety margin. In a perpendicular crossing scenario with simulated sensor delay, the system still avoids bubble violation, showing robustness to perception latency. Finally, we tested a symmetric deadlock scenario, where 2 obstacles approach simultaneously. A naive planner would freeze. Our logic injects a small y-axis bias, breaking symmetry and allowing the UAV to escape safely while maintaining forward progress. So far, we have completed problem formulation, plant modeling, and 2D static and dynamic avoidance validation. Future work includes extending the planner to full 3D navigation, integrating with ROS2 and Gazebo, and deploying the system on real hardware using hardware-in-the-loop testing. This project demonstrates how model-based design in Simulink enables safe, scalable, and verifiable UAV autonomy. Thank you for watching.